Andrea, please.
Okay. So good morning to everyone. Do you hear me? I guess so. Yes. So I'm the Andrea Mattioni. I'm the SR number 9, and I'm from the University of Bourgogne Franche-Comté, and my supervisor is Yann Legorec. And today I'm going to give a talk about a part of my PhD thesis, and in particular, I will talk about the strong dissipation feedback and therefore stabilization of a mixed ODE-PDE port-Hamiltonian system. So starting from some motivation, here we have 3 pictures. In the left one, we have a satellite with flexible appendages, and the control problem in this case can be stabilizing and orienting the satellite in a desired orientation, and at the same time stabilizing the flexible appendages that can disturb the motion. The second one is a wind tower that can undergoes to some flexible deformation, and a control problem is to stabilize these flexible towers such that we can augment the efficiency of the power conversion. And the last one is a micro gripper that has to grip some micro object and can undergoes to some flexible deformation, and we want to both position the micro gripper and stabilize the flexible deformation such to do the tasks that we have to do. So what we want to do is to find and to use a model that is able to include the rigid dynamics and the flexible dynamics of our mechanisms, and at the same time design a control law that is able to move first our mechanism and also to stabilize the flexible parts that we have also inside the mechanism. So we're going to consider a model that is composed by 2 parts, a finite dimensional part, so described by ordinary differential equations, that will describe the actuator inertia dynamics or the rigid dynamics of our system, that is interconnected with an infinite dimensional part described by partial differential equations that instead is going to describe the flexible dynamics. These 2 systems are going to be interconnected, and the input of our system will be in the finite dimensional ordinary differential equation. Another observation is that the output that we will have in our system are coming both from the finite dimensional system and also from the infinite dimensional system. So we assume to have as a sensor both coming from information coming from the finite dimensional part of our system and from the infinite dimensional part. So in this presentation, we're going to restrict ourselves on boundary control systems. So the infinite dimensional partial differential equation are going to communicate with the external environment or with through the boundaries. We're going to look at linear models and on first order partial differential equations. Moreover, we're gonna restrict ourselves on the port-Hamiltonian framework, and so the finite dimensional and the infinite dimensional system that we're considering will be written in the port-Hamiltonian framework. And moreover, the last assumption is that we're going to restrict our analysis on model without internal dissipation. So the only possibility of having dissipation in our system will be only injecting it through the control law. And so this because we want to understand how our control law is stabilizing our system without the help of external dissipation. In other case where the dissipation is actually not really helping in stabilization, this kind of problem should be treated separately. Okay, so a small overview. I will first introduce the class of port-Hamiltonian system that I will deal with. Then I will present a first control law that I will call strong dissipation feedback. A second control law that will be the strong dissipation feedback plus a position control term. Then I will do a comparison between the control laws that I presented. And finally, I will give some final remarks about the presentation and the ConFlex fellowship and my future plans. So the class of system that I'm considering are the interconnection of an infinite dimensional port-Hamiltonian system with a finite dimensional one. The infinite dimensional variable is described by Z and belongs to the space of a square integrable function on Rn. And the variable that is describing the finite dimensional dynamic is P and belongs to an Euclidean space of dimension n. Then the metrics that compose our system are H, that is a self-adjoint matrix that can be bounded from below and from above. P1 is an invertible and self-adjoint matrix, and P0 is a skew-adjoint matrix. The matrix M is called normally mass matrix from a mechanical interpretation. And in fact, we have the input that is equal to the inverse of the matrix multiplying the variable P that normally corresponds to a momenta. And therefore, normally, the output of our system, that is a finite dimensional output, corresponds to the velocity of our finite dimensional system. So we can define the state that is composed by both the infinite dimensional and finite dimensional part and the operator describing our open loop system. And the contribution of the infinite dimensional part on the finite dimensional part is given by this term that corresponds to the output of our infinite dimensional system applied on the finite dimensional part. While the contribution of the finite dimensional part on the infinite dimensional part can be shown in the domain of our operator. And in fact, a part of the boundary input of our infinite dimensional system is equal to the velocity of our finite dimensional system. So we define the input and output of our infinite dimensional system as a power conjugated variable. That means that the product between the input and the output will be a power. And then the total boundary input and boundary output operators are defined as a composition of the coenergy variables at the end of the spatial domain. So now we pass to the control design. What we want to do is to design a controller that takes some information from the finite dimensional and infinite dimensional outputs and is able to give back some control law that, in particular, in the first case, we want to stabilize the origin of our system when the system is described by the two variables that I described before, so Z and P, and we want that the states converge to the origin. And with the second control law, we augment the system with a new variable Q that will describe our displacement of the finite dimensional system. And we want again that our system is converging to zero as t goes to infinite. So we start with the first control law that we call strong dissipation feedback. And this control law is writes as following. It is composed by three principal terms. The first term is a classical dissipation term. The second term that is depending proportionally by a matrix Kp that is diagonal positive definite from the time derivative of the output of our infinite dimensional system. And then we have an additional term that depends proportionally on the output of our infinite dimensional system. We remark again that the input is not applied on the boundary of our infinite dimensional system, but on the finite dimensional system that compose our system. So here we have the closed loop operator. In the colored term, we have the control law that I introduced before. In particular, in red, we have the strong dissipation feedback term.
So, sorry, what is the boundary operator in your system? Is it you use a boundary control system?
Yes.
Correctly? So
yeah, the boundary operators are B1 and B2. A part of the boundary operator is this B1, and we have the other part of the boundary operation is B2 that we allow to be equal to zero.
Okay.
And so in the first boundary operator, we have the P contribution. Okay, so to analyze this kind of system, since we have this derivative, we want to get rid of this time derivative in the in the right half part of our equation. And to do so, we introduce a change of variable. And this change of variables is the following, such that the two blue terms are converted to the blue term in our system. And the red term is put on the left part of our left-hand part of our equation, such to define the eta dynamic. And therefore, the system can be rewritten in this different classical system. And in particular, we also substitute the P with a new change of variable in the boundary of our infinite dimensional system, such to make appear a dissipation term that will allow us to conclude about some stability results. Okay, so this is the picture of our closed loop system, where we have a finite dimensional port-Hamiltonian system, where the input of our system is on the eta dynamic, and that is interconnected with an infinite dimensional system, where we, through the change of variable, we made appear also the boundary dissipation of our infinite dimensional system. And so we have the two following results. First of all, the closed group operator A generates a contraction C0 semigroup in the state space, equipped with the standard energy norm that is composed by the infinite dimensional energy and the finite dimensional energy. And moreover, if we assume that the input and output of our infinite dimensional system are such that to satisfy one of these two inequality, and this two inequality means that we have enough control inputs on our system, then the state trajectory generated by our closed loop system is exponentially stable. So I give a very small sketch of the proof, and we consider a Lyapunov functional that is the energy of the infinite dimensional part summed with the energy of the finite dimensional part. We take the time derivative, and the time derivative is equal to a quadratic form with respect to the output of the infinite dimensional system, and a quadratic form with respect to the finite dimensional variable of our mixed port-Hamiltonian system. Then afterwards, after some computation, it is possible to find a function C of t that depends on time, that is always strictly greater than 0, such that this inequality is fulfilled. And therefore, since the Lyapunov functional is equivalent to the norm that is defined through the inner product that we defined before, it is possible to see that the semigroup that is generated is always strictly less than 1, and therefore we can conclude that our system generates a exponentially stable, that our system is exponentially stable. So now we add a new contribution to our control law, and to do so, we add a so-called position control. But what is the position control? To explain it, I take an example, and for example, I take a flexible beam that is clamped on a rotating inertia. This kind of system can be written in the framework that I used before, with the variable z that is describing the flexible deformation, and the variable p that is describing the momenta of the inertia of the motor that is connected to our beam. But what we want to do is actually controlling the position of this motor. And so we define a new variable q that correspond to the displacement, and in this case, in this particular example, correspond to the angular displacement of the motor, where the dynamic is defined as of course, the velocity coming from the inertia of the motor. So we now use a different control law that is actually the same as before. So we have the classical dissipation term and an additional term and the strong dissipation term as we had in the previous control law, but we also add in red a position control, such that we also want to control the position of our finite dimensional system. Then we write down the closed loop operator as before. We have the contribution of our control law acting only on the finite dimensional part, but now we have also a new dynamic q dot on which that we have to take into account for concluding about stability. Again, we make the change of variables that we did before, such that the two blue terms are converted in the blue term of the second closed loop operator, and the red term is put in the left-hand part, such to define again the eta dynamic. And again, it appears in the boundary of our infinite dimensional system some dissipation that will help us in stabilizing our our system. A new term that is appearing is also in the Q dynamic, a term that is depending on the boundary output of our infinite dimensional system. That was a thing that we didn't have before. So this is now the picture of the closed loop system that we are taking into account. And now we don't have anymore the input on the eta dynamic, but now the input so the contribution that is coming from the infinite dimensional system is in the Q dynamic and not anymore on the eta dynamic. And therefore, this system is not anymore a classical port-Hamiltonian system. But again, we still have the dissipation on the boundary condition of our infinite dimensional system. So we have a first result. If we assume that the control parameters are selected such to fulfill this inequality, then the closed loop operator A generates a contraction C0 semi-group in the state space capital X that is equipped with this new weighted energy-like norm, where this weighted norm is composed by the infinite dimensional energy as before, and a new term, a new quadratic term, depending on the finite dimensional variable that somehow are similar to an energy term, but it's not an energy anymore. And moreover, the operator A is a compact result. Since from this, a natural conclusion is that also the solution set of our system is pre-compact, and this will help us. It's a condition that is needed if we want to use the LaSalle invariant principle. That is the theorem that we will use for concluding about stability. So the other theorem is that if we assume that the distributed parameter part of our system is approximately observable with respect to the output YZ, and that the origin is the only equilibrium point, then if the control gains are selected such they fulfill these two strict inequality, then the origin is a globally asymptotically stable equilibrium. A small sketch of the proof, we define the candidate Lyapunov function as one half the inner product, the weighted inner product that I defined before, and taking the time derivative of the Lyapunov function and using the assumptions of the approximate observability of the fact that the equilibrium position is equal to 0, then we have that the largest invariant subset of the set for which the time derivative of the Lyapunov function is equal to 0 is only the origin. Then using the pre-compactness of solution and the LaSalle invariant principle, we can conclude that the origin is an asymptotically stable equilibrium position. So what is the difference between these two control laws that I presented, where there is one that allows to obtain exponential stability and the other one we only obtain asymptotic stability, but why using one or the other? So we take as an example a flexible beam that is clamped on a translating and rotating inertia. And as first thing, the control objective that we can fix is that we want to stabilize the system starting from an initial condition. But this sentence is a little bit misleading because of the term stabilize, because the other thing that we do have to say is what we want to stabilize. So we came up with two different objectives. So first of all, the first objective is stabilizing the flexible part of the mechanism starting from an initial condition, and the other objective is stabilizing the flexible part together to we want to orientate our mechanism in the position that we want. So for the first objective, we use the strong dissipation control law that I presented at the beginning, and starting from an initial condition, it is able to exponentially stabilize our system in an orientation that we cannot select. But using also the position control, we can stabilize the flexible part of the mechanism, and moreover, we can select the position and orientation of our mechanism such that we can position it in the place that we want. But of course, using the second control that I presented, we use the exponential stability, and so we don't know anymore the convergence rate of our system, but we gain the position control. Okay, so now some conclusions. In this presentation, I presented the strong dissipation control, and the strong dissipation control and position control, where in both of these control law we have the lack of direct control on the boundary of the PDEs, because for both of them we controlled our system through the finite dimensional system. With the first control law we obtain exponential stability, and but with the second control law we lose exponential stability, but we gain the position control. The future results could be on this topic, modify the strong dissipation and position control such to obtain also in this case exponential stability. Okay, here are the publications, and in particular the work that I presented today is taken from the publication that is under revision in Automatica, and the strong dissipation is the work that I present in the CDC 2021. And okay, so these are the segments that I did during my ConFlex, ConFlex project, and I've been for 2 months in the Thales Space Company, 1 month in Wuppertal under the supervision of Birgit, and 2 months in Twente under the supervision of Professor Swart. And okay, these are the conferences in which I participated in the last years. So as I said yesterday, I got my PhD degree on automating control in the University of Bourgogne Franche-Comté, the 23rd April of 2021. And my future plans are that I got a postdoc position in the GIPSA lab of the Université de Grenoble on the subject reinforcement learning control of nonlinear PDEs, with in collaboration with the professor Christophe Prieur and Paolo Frasca. Okay, so thanks for your